All right, so in our limits day 4, all right, like as promised, this list, the what we know, sort of gets longer and longer. We've gone over most of this at the beginning of today's class, so I don't want to spend too much time on that, but you'll notice that we've added to that list, how do limits apply to vertical asymptotes and end behaviors, and how do we find these graphically and numerically? Okay, so these are all really great questions for you to be asking yourself as you prepare for exams, or as you're thinking like, what were the main topics that we actually learned this week? Okay. Now this section is a particularly mathy section. Okay, so I think as soon as we see the word theorem, sometimes we get a little nervous, but my hope is to make this as sort of friendly as possible, but it is definitely a little bit more mathy than some of the other content that we've seen, okay? And so the 3 main things that we're gonna take away from this section, which we'll do some of them today, we'll finish it up on Monday, not a big deal, is the first one we're gonna look at is, what is the squeeze theorem? And how do we use it to evaluate the limit of a function? That's the one I hope to get to today. The second one we're going to take a look at probably on Monday is, what is the intermediate value theorem? And then the last one, which again we'll probably go over on Monday, is the epsilon delta definition of a limit. Okay, and so these are 3 sort of more formal ways of looking at limits. And we're going to start with that squeeze theorem today, okay? So for the squeeze theorem, you might hear it as the squeeze theorem, but there are folks who call it the sandwich theorem, and that is okay as well. All right, so both the squeeze theorem or the sandwich theorem are the same names for the theorem that we're going to take a look at right now. Now, I think I've mentioned this before, but I think, there's this piece of reading mathematics that is important to develop. And a lot of times we just kind of say, oh, I don't really know how to read the math book, so I just won't read it. But it is a skill that you can practice. It is a skill that you can learn and get better at. So we're going to do a little bit of that here right now, okay? So the squeeze theorem. It says, let f of x, g of x, and h of x be defined for all x not equal to a over an open interval containing a. If f of x is less than or equal to g of x and less than or equal to h of x for all x not equal to a in an open interval containing a, and the limit as x approaches a of f of x equals L, and the limit as x approaches a of h of x is also L, where L is a real number, then the limit as x approaches a of g of x is also equal to L. That's a lot. All right, I definitely would encourage you to read that over again. But before we sort of like panic about what is this all saying, I'm wondering if someone can tell me one thing that they know to be true in the scenario that we're considering. Okay, what is one thing that you can take away from this massive paragraph of math speak?
This doesn't work if L is not a real.
Oh, okay. So there's something about L having to be a real number. All right, so this L and this L has to be a real number. Yeah. Okay. What about this? How many functions are we looking at?
Exactly 3.
We're looking at 3 functions. Okay. See, we know so what's going on here. We've got an f of x, we've got a g of x, we've got an h of x, right? We're looking at 3 functions, and maybe I should choose different colors for these, but in these 3 functions, what do we know about the three functions? Are they just like any random functions?
If we're considering this theorem, we know that they have a relationship.
Okay, and what is that relationship?
F of x is less than or equal to g of x, less than or equal to h of x.
Okay, so h of x is sort of has the biggest y values out of all of them. And g of x is like the middle, and f of x has all the smallest y value. Okay, now there's a great question here. Would there be an asymptote because x does not equal a? And that's no, but I 100% get where you got that from. Okay, and we're going to unpack that a little bit more. All right. Let's see, is there anything else that we can say from here? Anything else that's going to be true anytime we want to use this particular rule?
A is some value of x.
Great. Okay, I got two different things here, which I like both of them. Let's write here. A is an x value. Okay. A is an x value. And then Joey said the limit of f of x and g of x are the same when x does not equal a. Almost. We know that the limit of f of x and the limit of h of x are the same. So if the f of x and the h of x have the same limit, then we know that g of x will also have the same limit. Okay. Now that is all very fancy math talk, right? Very fancy. And I think you folks did a great job of stepping up to the plate and trying what that to describe what that means. Okay, but so we call this the squeeze theorem, but we also call it the sandwich theorem. I kind of like sandwich theorem a little bit better because I like to eat sandwiches. And so it makes it easier for me to visualize like what's actually happening, okay? And so what we can think about if we want to make this a little bit more friendly terminology for ourselves, yes, exactly. We have a sandwich happening here, okay? So if we know that they're in order, f of x, g of x, h of x, which function or functions would represent the bread of your sandwich? Yeah. All right. So we could say then that h of x is like the bread, and then f of x is also the bread of the sandwich, okay? I don't know how many of you are gluten-free or low carb or whatever the new eating things are, but if we think about a traditional sandwich, we've got two pieces of bread. We've got our f of x and our h of x, because those are, yeah, exactly, because those are sort of on the outsides, right? And your filling of choice is going to be your g of x. All right, if you're going to have a bologna sandwich, that's 100% on you. You want a Nutella sandwich, also your choice. Whatever that filling is, we want that filling to always be between the bread slices. Okay. Now, imagine your favorite sandwich. All right. Now, for the sake of this theorem, we're only going to think about one filling, right? Because we only have one function in there. But think about your favorite sandwich. All right. So mine is going to be, I don't know, what have I been eating lately? Peanut butter. All right. So I've got a peanut butter sandwich. My g of x is the peanut butter, and I've got my f of x and my h of x that are the bread. Now, let's say that I'm holding my sandwich and I just squeeze the sandwich together. All right. What happens will my fingers at some point touch? Will the two slices of bread touch at any point if I keep squeezing this sandwich? Or whatever your filling might be. And if we think about that, we're like sort of squeezing the two outside layers together. At some point, all three pieces, the bread, the other bread, the peanut butter, are all going to sort of exist in the same space. All right. And that space is what we call our limit. All right. So they're getting to the same y value. And if the outer parts are getting to the same y value, then the inner part also has to get to the same y value. Okay. So that might be like a more fun way to think about this sandwich theorem. But what I'd like to do is we're going to sketch a quick picture. I bet we can do this without Desmos. But we're going to call our f of x to be negative x squared. We're going to let h of x equal our positive x squared. All right. And so let me sketch this real quick. Whoops. Right. I know you all know that h of x is just going to be an upward facing parabola. What can you tell me about negative x squared? It's going to be a downward facing one. Perfect. Okay, so we've got our h of x, we've got our f of x. Now, before we go any further, is the blue function always greater than or equal to the orange function? Let's make sure that's true. All right, so I think when we look at this, we'll notice that blue parabola has always got a bigger y value than the orange parabola, except where? Where are those two not necessarily greater than? Yeah, at x equals 0, they're actually exactly at that same place, okay? So now let's draw in our g of x. And g of x, we said, is the cubic function, and we kind of sketched one of those earlier, but the cubic function is going to look something like this. Okay, the cubic function is going to look something like this. Is the green one always between the blue and the orange?
Yes.
Yeah, that green one is always between the blue and the orange, okay? So because our picture matches this statement that f of x is less than or equal to g of x, less than or equal to h of x, we can do exactly as someone said in the chat, we can squeeze it to 0, okay? So in other words, our a in this case is 0, and this is an x value, all right? What is the y value we would expect the green function to have at x equals 0? Like, let's pretend we didn't know. Yeah, we would assume that because this goes to 0 and this has a y value of 0, that if you go right in between them, you should also have a y value of 0. Now that's a lot of zeros, but I just want to make sure we're aware that the first 0, that a equals 0 is an x value, and the L equals 0 is a y value, okay? All right, so visually and conceptually, that's kind of the gist, okay? But what does this actually look like when we take a look at a problem, all right? let's see one example. All right. So in this particular question, all right, we've got the limit as x approaches 0 of x squared cosine 1 over x. All right. Now let's say you got this question on an exam or a quiz. What would your first step be? Like, what would you try first to find that limit? Yeah, exactly. We would try substitution, right? So let's do that. We've been a little lazy on doing that for the sake of all the other techniques we're learning, but let's plug in 0 right now and see what happens. 0 squared cosine of 1 over 0, okay? 0 squared gives me 0 times cosine of, what does inside the parentheses go to?
Undefined.
Yeah, cosine of undefined. Well, if cosine is undefined, or if this is undefined, and then we're taking cosine of undefined, it doesn't seem like we're going to be able to get to a number, right? So this is a case where we've tried substitution and we're like, it's not helping us. And we have a quadratic, like we have an x squared, but I don't see anything that we can factor. There's no square roots, there's no conjugates, there's a fraction, right? 1 over x, but it's not like a fraction inside of another fraction. Instead, it's like a fraction inside a different function. Right? So seems like the techniques that we've learned before aren't going to be helpful. And so that's what this sandwich theorem or the squeeze theorem is all about. It's like, how do we figure out another case of a limit when the other strategies that we know don't necessarily work? All right. So let's start with this, okay? Oops. What do we know? Your very first line in a question like this should be something that we know is true for some part of this function, okay? Now, I'm wondering, can someone tell me what's true about cosine? Like, tell me some things you know about cosine. Isn't it bounded on a graph? Tell me more about that. What do you mean by bounded on a graph? Okay, it stays between y values. Can you be more specific? What y values does it stay between? Yeah, what's the relative minimum? What's the relative maximum? It is a wave, but what are those y values? -1 and 1, yes. Okay, so this is what we're gonna do. We're gonna use that and we're gonna start to build our sandwich. And so we're gonna say that -1 is gonna be like one slice of bread, and that's less than or equal to cosine of x is less than or equal to +1. Okay, so we are starting to build our sandwich. Now, this next step, I think, is going to be a little weird for us to think about, but ignore this x for a moment. Okay, ignore this x for a moment. And let's say I just have cosine of something. Cosine of anything is going to always be between -1 and +1. It doesn't matter what that thing is. Cosine of anything will always be between -1 and 1. Is that something that we buy? Yes, no. Yeah, okay, so cosine, no matter what I'm cosigning, that thing, the result will be between -1 and 1. And so we originally had the x here. But in my question, I have 1 over x. So here's what I'm going to do in this next step. -1 is less than or equal to cosine of 1 over x is less than or equal to +1, where x is not equal to 0. Okay. So I started with x, but I was able to generalize that and say that no matter what I'm cosigning, that thing will still be bounded by -1 and 1. Now, why would I choose 1 over x? I chose 1 over x because that was in the original question. Okay, I chose 1 over x because that I'm trying to get to the function in the picture or in the equation. All right. If I had 2 over x in the function, then I would have made the light blue part 2 over x. Or if I had 10 over x in the blue part, I would make the other blue part also 10 over x. Okay. Yeah, so 0 is like our A value here. Exactly. Okay. And so that's it. This is exactly why someone said earlier, oh, is it a vertical asymptote? It's not that. It's just that sometimes when we plug in that value, it might give us sort of a messy, undefined situation. Okay. All right. So we've got this part so far. We've got cosine of 1 over x. But now we need an x squared to make this middle part match that function. Okay. So here's what I'm going to do. I'm going to take the entire inequality and I'm going to multiply everything by x squared. Negative x squared cosine of 1 over x positive x squared. Right, so multiply by x squared. Okay. Now, why did I multiply by x squared? Because I wanted to match what was in the question, x squared. Okay. Now, here's what we're going to do. We're going to take a look at the bread pieces that we've made, and we're going to find the limits of the bread pieces. Okay. So what is, when we plug in 0 for x, we're going to get 0 over here, right? 0 squared is 0, -0 is 0. We're going to skip the middle part, or the filling of our bread, or of our sandwich, but let's go to the other slice of bread, x squared. When we plug in 0, what do we get? We get 0. Okay. What number is between 0 and 0? 0. Exactly. All right. So what this means is this is our filling in the sandwich. This must also go to 0. Since the bread goes to 0, the filling also has to go to 0. Okay. Yeah, a lot of the examples that we've chosen here go to 0, but some of them go to 1, so, or other values. So it's not always 0. But I think so this is actually sort of what we call a proof by construction. So we are constructing something. And a lot of times when we're constructing things, we want to use the nicest values possible. And so we end up with like zeros and ones and things. Okay. All right, so I'm going to actually stop here. Let me make sure I can find my window. Boop, boop.